We'll take a look at statistical analysis tasks 4.25 and 4.26 next. We're looking at pump shaft length L2, and the first question is, if the true mean L2 is 50 millimeters, what's the probability that your results from section 10 are by random chance alone? And then 4.26 asks us to find the probability of a measurement of 52 millimeters and the probability of measurements between 51.95 and 52.05. So we'll take a look at the data and try to work that out. So first we'll go ahead and make a pivot table. And in so doing, we'll add measurement components, and then we'll add values, numerical values. We'll add the average, standard deviation of the population, and we'll also add the count. We'll filter this data on measurement components, and we'll only show pump shaft length L2. And then we'll also add a filter for section. And we'll only keep section 10. So with that, we have our data here. We can get rid of the grand totals. So for pump shaft length L2, we have a mean of 51.490, a standard deviation of 2.061 with 29 measurements from section 10. And we have what we'll call X prime given as the true mean, millimeters, and that is 50, okay? We're asked to find the chance that our result is random chance alone, the probability of our result being random chance alone. So one first approach is to use a z-score where we compute the difference between the mean, the true mean, and our mean, and divide it by the standard deviation. And we get with that minus 0.72, minus because our average is actually greater than the true mean. And so we could look that up in a z table if we were trying to find out the probability that our result is as extreme as that. What we could do is go ahead and look at a z table and say minus 0.72, which is really just 0.72, and we can get the probability of that occurring one-sided is 0.2642. And so come back here. So P Z one-sided 0.2642 or 26.42%. Now, if we want to consider that probability, we really need to multiply by 2 if we want to find a value that's as extreme as that on either side. So we can get the probability of a value between plus or minus 0.72 away from the mean is 2 times that. And so that's 52.84%. And so looking at the text real quick, we can see that what we're doing is we're computing this value, multiplying times 2, and we're really computing the number of standard deviations away from the mean we are. And so here our Z is 0.72. So we're less than 1 standard deviation from the mean. And so we find that 52.84% is the area under the curve within 0.72 plus or minus Z from standard deviations from the mean. And so that result seems fairly likely. So in other words, the variation that we're seeing and that we're observing is probable. It's within reason. It's not at all improbable or unlikely to occur. And so the probability of being outside of that range, just the complement of that, so is just 1 minus, and that's of course 1 minus 52, and 47.6% could be as extreme as our 51.49 measurement. So again, that's our level of variation observed here, even with a true mean expected of 50, is fairly likely to be just random error, random variation alone. It's not at all unlikely. Another way to look at that is more of a hypothesis test. And so with the hypothesis test, we'll scroll down on the textbook and take a look at that. What we're going to do is establish a null hypothesis and then look at whether or not we reject that null hypothesis, similarly by computing Z values for critical values used for a Z test. In this case, we'll use 5%, and so 95% probability within the not rejection range. And that means our critical thresholds are 1.96 plus or minus for Z. And so the idea of a hypothesis is a statement that something is believed to be true. So the hypothesis in this case is the difference between some observed or measured value, the mean that we get of the population, is an assumed, and compare that to an assumed behavior, is small enough to be considered due to random chance alone. And so that establishes our null hypothesis that the variable is a random variable that's normally distributed and has a mean of 50. And so we can come up with a hypothesis test for that. A Z-test is probably the simplest way to do that if we assume that the standard deviation that we have is the actual standard deviation of the population. And so it's a very similar calculation. The sample mean minus the reference value, the true mean here is x naught divided by standard deviation divided by square root of n. And so that we evaluate that at some desired level of significance alpha. And so we'll use alpha of 5%, but because it's a two-tailed rejection region, we split that alpha into 2. And so that gives us for the Z-test, we're looking for Z's that are more than 1.96 standard deviations from the mean to be considered something that is significant. Or if it's significant, we might then say, okay, we're going to reject the null hypothesis and assume that there's some other thing going on, perhaps a systematic error that's causing those results. So going back to the data, that's not a big change for what we're trying to do here. We just take that Z value and we can divide it by square root of n. We can also just take the absolute value of it. So in this case, we could say 51.49. She'll put parentheses around that. 51.49 minus our x naught divided by our assumed population standard deviation of 2.06, and then divided by the square root of the number of samples. In this case, we have 29 cases. And so we get a Z-test critical value for that of 0.134 0.13 is probably good enough to for the significant digits that we have. So our critical Z values for 95% or for alpha 0.05, which is also saying 95% within the not rejection region. Our critical thresholds are Z equal to plus or minus 1.96. And so our Z test of 0.13 is well within plus or minus 1.96. And so again, this result is likely to be by random chance alone. It's not at all significant that there's some systematic difference between the true value and the measured or observed value of the data for this particular problem. So that's the first problem that we were looking at, and the others are related. So compute the probability of a measurement of 52 millimeters and the probability of a measurement between 51.95 and 52.05. Okay, and so I think what we're really here is the probability of at least 52 millimeters. If we go back and look at the original measurement here, or the original shaft, we have L2, which is this end measurement here, this length from here to here. And if we look at the geometry that we're talking about, we do expect for that to be 52, according to the drawing. So what's the probability of our measurement being at least 52? And then what's the probability of it being 52 plus or minus some range? I think it was 0.05 that we're asking for here. 51.95 and 52.05. So we'll go back to the data. And so our X of probability of X, we'll put it this way, 51.95 is, X is greater than that, is less than 52.05. That's our question, what we're trying to find. We're also trying to find the probability that X is at least, so let's call it greater than or equal to 52. And we can also use equal signs here, greater than, less than, equal to, in this question here. Okay, and so for this, we can calculate Z values as well. And so we'll go ahead and compute Z value for 52. And so here we have I'll say this equals -52 minus this guy divided by standard deviation. And so we get 0.247, 0.25, come over here, and we see 0.25. It's this guy right here. That is a probability one-sided of 0.0987. Okay, so our P 52. .987. Okay. And so that in part answers the question. So that is the range between the mean and 52 is in percentage 9.87%. probability. Now, if we're asking about between a certain range, we can take, we can compute intervals for that. So we'll have Z, we'll call it low, and Z high. And so here we'll just compute this as equals 51.95 minus mean divided by the standard deviation. And that gives us 0.22. And for the high, we have 52.05 minus the mean divided by the standard deviation. And that's 0.27. So the probability for 51.95, we'll look that up on the Z table, 0.22, 0.22 right here. Put that back here. And then this guy, P, I guess we can also call it I, which is 52.05 or 0.27. 0.27, that's this guy right here. And so the probability that the measurement is between those two values is just the difference between these. So we have equals this minus this. And so the answer to our question is there's a 1.94% chance or probability that the measurement is between 51.95 and 52.05. And here the measurement is x less than 52, one-sided, 9.87. And so depending on, it's between the mean and 52. And so if we really wanted to give that as a probability of it being less than 52, we really need to add another 50% here. And so we could put that in as 1.87. Where is it? Plus 0.5, and that would be 60% probability that the value is at least 52. Okay, based on the shaded region and the way that we're using the one-sided Z table here. So in that case, I added 50% for here to here, and then the Z1 value is right here for 52. So that answers the questions posed here in 52.5 related to pump shaft length L2.